Today we're going to be studying mathematics.
And emerges from the second mirror.
These words sound
Be your teacher for today.
Hello class, my name is Vincent. How do you find the previous class? I hope you are enjoying it. Today is another interesting topic: work, energy and power. I want to believe that all of you have been working at home even before now. You get yourself prepared for you to bathe this morning. You go to the bedroom, you carry some little things, that is work. Then energy is already residing in you that you use to carry out your work. So as we look into this topic, it's a topic that you will get familiar with, and it's not too abstract. It's something that we do every day. By the way, what is work? What is work? In physics, there's a way we approach this topic, but any other person can tell you work is my activities, or what I do, or to earn one thing or the other. That's for the, but when you come to physics, we look at work and we define it as, before you can say you do work, we must actually put some parameter in place that actually see you that you have also done a work. So right there, I want you to do a little work for me. Just carry your book from that point you place it now, shift it just 5 meters away from you. If you have done that, you have worked. Because if you have worked, you will have done something, and we want to see what you have done. And by moving a book from one point to the other, which is no longer in the original place, that person has worked. What makes us to know that the person has worked is that you have used force, you have used energy, force, to carry the book and put it in another place, and you are able to carry the book through a distance of 5 meters. So that is work done. Work has been done. But when I ask a boy to carry a particular thing and the boy cannot carry it, work has not been done. Do you understand what I'm saying now? Work has not been done. For work to actually be done, you actually move the particular body from one point to the other, a distance far apart to the other. Then you apply force. So the product of force and the distance give us what we call work. So by that, we can now define what then is work. So work is the product between force and the distance. So work is the product between the force and the distance. The force you apply, so it's the product between force and the distance. That is when you say you work. So to actually measure it, we want to see there is a change in the location of the object through a particular distance, and you have used effort to do that. So that is work, and work is measured in joule. The unit of work is in joule. It's in joule. There are various ways you can do work. You have seen a crane lifting a load from the ground level to the top, whether they are building one particular bridge or the other, or a very tall building. So a crane is used. We have also seen that a boy can tie a rope to a load and begin to drag the load, and the boy is actually doing work. So but different way and different perspective we do work will make our formula to be adjusted, because we don't have the same formula. Like I told you, is the product of force and distance. But in case where the work you are doing is making an angle, you have to consider this angle and put it in place. So that will change the formula. So let's directly move to the formula and how to get used to them. So work done is force times distance. So the unit of work done is joule. So denoted with letter J. Now, illustration 1. Consider a boy pushing a load of 5 kg horizontally. When you have a table here, so this is a boy, this load is 5 kg, this is the boy pushing the load of 5 kg. He moved from this distance to this distance, that is the x. This is now where the load is. Now this is still 5 kg load. So the work done now, is the force times the perpendicular distance from the point of action. So the force the boy apply multiplied by the distance x, and the force is F, the distance is x. So this gives us the work done in that case for illustration 1. The formula begin to change if the direction is changing. It's no longer parallel. In this case now, the boy is pushing like this. That's how the boy is pushing, parallel to the horizontal axis. That is why the formula is that. So by the boy decide to put tangentially at a particular angle, this will not be the way the formula will be. The formula will make a change, a little change from that. So let's take a look at that. Let's call that one illustration 2. For illustration 2, you can see the mechanism that the boy has applied in pushing this load now. It's a system of mechanism making the load easy for him to push. So he attached a rope to the load and is pushing the load in this direction. This is the rope now using to pull this load, and it's in this direction. And this load will be moving like this with this arrow. That's the direction the load will be moving. So the way the load is moving with the way the boy is pushing, applying the force as a kind of angle between the two lines. So you have to consider this angle. So in calculating the work done now, so the work done, so you have to be the force times the distance, the cos of that angle for you to get that angle. So the factor here, this cos theta here, is actually the horizontal component force that we apply. So the total force now, since the force is horizontal, the total force is this F cos theta, S is just the displacement there. So the total force now is this F cos theta, that is total force. Not in this case now, the total force here is F. But in the second one now, the total force is F cos theta. So this F cos theta is actually the F, which is our horizontal force. That's a total horizontal force, because this is like a vector component which you have to resolve horizontally and resolve vertically. So the resolved solution of this force, because this force has component, has Y component and has S component. So since this load is moving along the S component, we actually need the force that is pushing it along that S component, which is F cos theta. So this one will now replace this F in the initial formula F, making it to become like this. So that's how to handle such problem when it comes to you. Now that's all about work. Now when we talk about energy, people define it as ability to do work, as the ability to do work. Some other people say is the capacity to do work. And energy and work done, they are not different, because the unit of energy is joule, the unit of work is joule. So we can now conclude and say work is equal to the energy. Work is equal to the energy. So now energy is denoted with letter E. So we can have potential energy and kinetic energy, which is half mv square, potential energy mgh. The two of them is also work done, it's also energy, because some other time you can be required to carry something from the ground and take it up. As at such time you are doing work against gravity, so your formula is mgh as at that time. At such time you are doing work like that. So if they ask you to calculate if you are carrying something vertically against gravity, so your potential energy becomes your work done that you are going to do. So this kinetic energy, because you are doing work against gravity, so this is the kinetic energy that comes as a sort of motion of a body. So energy and work, they are both the same. So that one take us to the concept of power. So what is power? Power is the rate of energy expended over the time. The ratio of the rate of energy expended to the time. So power. So that's the expression for power. So all you need to do is put all the formula for both energy and work done, place it here, divided by the time. That gives you power. So the rate of energy expended over the time gives you power. So and the unit of power is watt. But in a bigger form, you can have the gigawatt, the megawatt, and the kilowatt. Those are the bigger form of energy. So that is we have also measure it in horse power. That's what you measure in. You measure it in horsepower, you measure it in watt, in gigawatt, in kilowatt, in megawatt. So we are going to see a little bit calculation under these three concepts: work, energy, and power. Work example 1. A boy pushes a bus through a distance of 20 meters with a force of 500 Newton. Calculate the work done by the boy. If you look at this question, of a truth, you will know that work must be done, because there is force and there is distance. And once there is force and there is distance, work must be done. We can calculate the work done. So now solution. So what we are given, so we are given distance x 20 meter, we are given force 500 Newton. So you have to calculate the work done. The formula is simple: force times distance. The force is 500 times 20. So work done is equal to force times distance. We have given force, we have given distance. Replace them in the formula and multiply them. It gives us this, which is 10,000 joules. That's the unit of work, 10,000 joules. Work example 2. A mass of 15 kg is lifted through a height of 20 meters. Calculate the work done on the mass. The value of G is to be taken as 10 meters per second square. The usual format is that you list out what you are given first. That's the approach to physics. So what you are given is mass of 15 kg. The height of 20 meter, and acceleration due to gravity 10 meter per second square. So what we are looking for, work done, W. So what we are looking for. So in this case now, our work done, W, work done, so is mg is force times distance. But I need to explain something for you in this formula, because force is not given here, and at the same time I can tell you that force is given. You must know what this parameter F stands for. Another way you can express your F, it is not all the time they will give you FF. F can be expressed in another form, another way of doing it. So you have to know that F is the same thing as mg, and you have to know that your d distance is the same thing as your height. These little things, you must put your mind to them, so that when you get to a problem, you will not say that you are finding it so difficult to solve or very hard for you. So it's a little replacement we are going to do now. Since we know that now, we now say work done, do the little replacement. So instead of F now, I put mg there. You are transforming the formula gradually now. Instead of F now, I put mg there. So instead of D now, I put H there. So why we are able to do that is just because distance and height, they are the same thing. They have the same unit. I need to remind you again, in physics, when parameters have the same unit, you equate them. A can stand, if A have the same unit with B, A is equivalent to B, is equal to B. So we can put it there. You are permitted to do that. That's what you must know when you are playing with physics. So I have my mass now, 15 kg times the 10 times the height, which is 20. So multiply this. So when you carry out the multiplication, 15 times 10 times 20, it gives us the result of 3000 joule. 3000 joule. That is the second example on work done. Work done. So let's look at example on energy. Example on energy. You will find out that it's related and is similar to what we have just done. So the question that I've given unto you on the board, I can put it that calculate the energy. You do the same thing, remove work done and put it there. It gives you what is you are asked to calculate. But then let's still see example on energy. So work example 3, a bullet of mass 15 kg has a speed of 20 meters per second. What is its kinetic energy? This example falls under energy. So solution, we are given the mass 15 kg, what we know now. Now the velocity 20 meters per second. So we are looking for E. Is what we are looking for. We don't know. So recall that E equal to half mv square. So our E equal to half. The mass is 15 times the velocity is 20. You square it. So you have the mass to be half of 15. So 400. So this one goes, I have 200. 15 times 200. 15 multiplied by 200, the result will be 3000 joule. That is for the problem. That's the solution to that. So the next example will be example 4, and that will be on power. A girl whose mass is 20 kg climb up 25 steps each of height 15 cm in 10 seconds. Calculate the power expended. So what we are given is the mass, is the height, is the time. We are looking for the power, and we are given the value of G. Now what we are going to quickly do is to convert this one to meter by dividing by 100. So our 15 divided by 100, that gives us 0.15 m. Convert it to meter. Convert it to meter. So the standard unit of length must always be in meter. Meanwhile, you may come across problem that they will not give you the problem in meter directly. Is your duty, or you are expected to convert everything to the standard. Mass must be in kilogram. If it is given in gram, you bring it to kilogram. Length must be in meter. If it is in meter, you make it to be in, so if it is in centimeter, you bring it to meter. So time, if it is hour or minute, you bring it to second. So these are the things we work with. So now we can now apply the formula now. So we have power. Our mass is 20. Our G is 10. Our height now, because they say each of height 15 cm, that means one staircase is 15 cm. So 25 will now be 25 times 0.15 all over the time 10 seconds. So we now have this one, we eliminate this. So now power to be 20 times 25 times 0.15. This one gives us 75 watt. That's the unit of power. Since we are talking about energy, I still want us to pay attention to conservation of energy. How do we conserve our energy? With any type of energy, how do we conserve it? Conservation of energy. And at what point in physics can this one come in place? Number one, when you see a free falling body, it will obey this law automatically. It's a principle. And when you see a body that is performing simple harmonic motion, it will also, e.g. simple pendulum, it will obey this principle. Now those are the two areas in physics where this principle will be obeyed: free falling body and simple pendulum. Example of simple harmonic motion. So what do you actually mean by saying conservation of energy? So we have mechanical energy, which is potential and kinetic. And these two energy potential energy can become kinetic energy, and kinetic energy can become potential energy. And at what point? If we follow a free falling body, when the body is about to reach the ground, the kinetic energy at the top is now equal to kinetic energy when the body is about to reach the ground. So consider the body falling from this particular height through this distance and is coming down to this place. At about hitting the ground, the body here is not moving yet, so the energy here is potential energy, mgh. That is that. Now moving from here to here, the kinetic, this potential energy here on reaching the ground, when it's about to hit the ground, will become kinetic energy, half mv square. So if this is point A and this is point B, so B A is equal to B. That's what we are saying, because of the law of conservation of energy. So the law will hold. Now if they ask you what is the energy of the ball here, you can tell them, you can use this formula or use this formula, because both of them will be the same. Both of them will actually be the same. It is at this point you can be permitted to do that. That I can replace my formula for potential to be kinetic. The moment this body hit the ground, it has turned back to kinetic. So for the formula to hold, you must not allow the ball to touch the ground. It's when it is about to touch the ground, that is at that point the formula will work. So as at that point, we say that is what we call a conservation of energy. You can also see it in a simple pendulum. This is a case of a free falling body. For simple pendulum, simple harmonic motion is like this. You have a body like this, then you have it like this, a body rolling like this here. So at this point, when you are still holding it, is potential energy, mgh. This is actually the height here that will account for our h. That is our height here is this h. So the mass of this pendulum ball is there, the gravity. So at this point, so when it get to this place, it become kinetic energy. So between this point A and point B, the formula hold. So this is equal to this. So I can say mgh is equal to half mv square. Conservation principle hold. So now in between this point and this point, point D, then you now have a little, you now have the height to be like this. So the principle also still work for point D. So potential energy will now be equal to, at this point, you have to be very careful, at this point now, the energy here is potential and kinetic. Not like this point. In this point, the energy here is purely kinetic. The energy here is purely potential. But the energy between kinetic and potential is both potential and kinetic. Though the law still hold by saying that energy A equal to D. The energy is in A is mgh, but not to get confused with this and this. We can say this one is h. We can say from here to here is h1, because their height will not be the same again. So equal to mgh1 plus half mv square. Then the v here is different from the v here. That's going to be v1 is different from the v here. So put all those things into consideration. So with this equation now, the law holds between this point and this point, and the law also holds between this point and this point. So at this point, if a body is here and a body is here, the energy here and the energy here, they are the same. If a body is at this point and it comes to this point, although the energy here is both potential and kinetic, but it must still be equal to potential. All we are just saying about the principle is that at this point and this point, they must be equal. The energy must be equal. Irrespective of the transformation that has taken place, they must be equal. That's what I'm going to do. So we just look at one problem under this conservation of energy. Example 5, a ball of mass 1 kg is dropped from a height of 7 meters onto the ground. Calculate its kinetic energy just before impact with the ground. B is kinetic energy and velocity when the body is at height 4.5 meters to the ground. So we have to follow this question carefully and illustrate it on the diagram first. Show how the whole system work on the diagram first. We have a ball of mass 1 kg. It's dropping from a height of 7 meters onto the ground. So let's assume that this is the mass of 1 kg. And from this point to this point, this is our height of 7 meter. That's our height of 7 meter. Now it's coming to the ground, and we are told that we are to calculate the energy just before it hit the ground. That means you will not allow the ball to hit the ground. That means let's just say at this very point about to reach the ground, that is where the mass, the ball will be now, 1 kg. So at that point, at this point, before impact, potential energy and kinetic energy, based on the principle of conservation of energy, must be equal. You have to bear that in mind. So any of the two formula now you can now use that will work for you, since the two of them are equal. So we have mgh at that point will be equal to half mv square. That's what will happen at that point. So I will now look at it. Can I use this? No, I cannot use this, because in the question I don't know velocity. I can't use it. But understand that whether I use this or I use this, it gives me the same answer. Just of this statement, before impact, meaning that before reaching the ground, close to the ground, that is the meaning. So as at that point, this and this are the same. So meanwhile, they asked me to calculate kinetic energy, but I can use this. I can say everything now is equal to kinetic energy. Why? Just because I know the condition before impact is that kinetic energy must be equal to potential energy, or potential energy must be equal to kinetic energy. So the two of them, I can call them to be kinetic energy. So I will use this one now. I have the mass. The mass is 1. The gravity is 10. The height is 7, equal to my kinetic energy. I will still say again, I'm using to be equal to the kinetic energy, though this is the formula for kinetic energy, while this one is formula for potential energy. But for the purpose of conservation of energy, then the two of them are the same. They give you the same result. Here now we have 70 joule equal to kinetic energy. So our kinetic energy is 70 joule. We are done with first part. I done the first part of the question. Now going to the second part. Now we are to calculate its kinetic energy and velocity when the body is at 4.5 meter to the ground. 4.5 meter to the ground. So we are going to measure 4.5 meter from the ground. So since the whole height is 7 meter, so let's say to the ground now. This is the ball now here for the second case. This is second case now to the ground. The distance from here now to the ground is 4.5 meter from here to here. Then that means from here to here is 2.5. That is 2.5 meter. If you add them together, this one will give us 5, 6, 7, making a complete length. So that's what I'm going to know. So our focus now is this very point. That's our focus. That's at that point. So to the ground, our G still remain the same. Now I told us the other time that whether here or here or here, the law of conservation still obey. So for B now, apply the law of conservation to, let me call it point B. Let's say we point B to that point B, meaning that the energy here, mgh, and the energy at point B now, let's call this one point A, mgh, where this our h is the total height. Like I told you, at this point now, the energy is not kinetic, is potential and kinetic. So you have to consider that. So my kinetic energy here will be mgh1, I denote the H because the H I'm using for this will be different from this. This is the total H. Why I'm using this H for that. Now, if you do that plus the kinetic energy, this is now what we are looking for. I don't need to express it in half mv square. I don't need to do that because that's what I'm looking for. I represent with the kinetic energy. So this plus this must be equal to this. So all we need to do now, mgh minus mgh1 equal to kinetic energy. So the mass will be the same for this and this. Mass will not change. Mass is constant everywhere, whether it is thrown up or it's on the ground, the same mass. Now, the mass will be the same, the gravity will be the same, only the height will differ. So the height we are using here is 7. We now have mass is 1 times 10 times 7. Here, mass is 1 times 10 times to the ground now. This height now, 4.5 equal to K E. So this gives us 70 minus 45 equal to K E. So by the time you subtract this one from this, we have 30, 40, 25 equal to K E. So 20 K E, the kinetic energy is 25 joule. So 25 joule. The velocity now, since we have gotten the kinetic energy, you can now say kinetic energy now, velocity now, velocity, kinetic energy is half mv square equal to 25. We have gotten the kinetic energy. So we are looking for V. So if you cross multiply here, mv square is equal to 2 times 25. That's what we have there, 50. So divide here by m, divide here by m. So we have v square equal to 50 m. So we have v square is equal to 50 over 1 is equal to 50. So v equal to square root of 50 meter per second. So these problems, they are given to you to practice it on your own at your free time. These are the problems you need to solve yourself, and if you have any issue, reach our number, the WhatsApp number on the screen displays, and forward your challenge to us, and we'll get back to you as you solve this problem. The first problem is a motorcyclist traveling at 45 meters per second overcomes an air resistance of 200 Newton. What is the power of the engine? 2. A body of mass is 0.6 kg is thrown vertically upward from the ground with a speed of 20 meters per second. Calculate 1. Potential energy at the maximum height reach. 2. Kinetic energy just before hitting the ground. The value of G is given as 10 meters per second square. Number 3, a man whose mass is 75 kg walks up a flight of 12 steps, each of 20 cm high, 20 cm high in 5 seconds. Find the power he developed in watt if G is given as 10 meters per second. The fourth problem is a bullet of mass 10 kg is fired into a fixed block of wood. If the velocity of the bullet is 60 meters per second and the bullet penetrated is 0.04 meter inside the block, calculate 1. The kinetic energy of the bullet. 2. The resistance force offered by the block. It will actually help you to facilitate your understanding and to actually you yourself can actually measure your level of your understanding as you go through them. So with this, we come to the end of this topic. So as you are doing it, if there's any difficulties you come across, the number is displayed there on your WhatsApp on the screen. It's a WhatsApp number. You can reach us as you face any challenge as you go through this example, through this problem.